Hello everyone and welcome to the class of Natural Gas Engineering. In today's lecture, we are going to continue our discussion of Introduction to Natural Gas. So, I named this topic as Introduction to Natural Gas 2. Before we go ahead with the plan of discussing the phase behavior, let us summarize what we discussed in the last class, Introduction to Natural Gas 1. In that class, we discussed several aspects of natural gas engineering from its exploration to its business. We started with natural gas definition, share in the world market. So, how natural gas as a hydrocarbon source or as a fossil energy source is going to play a major role in the meeting of world energy demand as well as for a particular country. How the future can be predicted for the natural gas. Several reports are published. Those reports provide us the guidelines based on certain models, which particular component of energy is going to lead in the future and in which sector the major contribution will come. We discuss these aspects with respect to natural gas in the domain of fossil fuel energy or in a carbon constant world. We also discuss the utilization of natural gas, means from its feedstock as well as fuel properties, how this can contribute to several sectors in the form of direct energy or indirect source of the energy. Like for the electricity, natural gas can be used as a fuel. Similar for fertilizer and petrochemical synthesis, natural gas can be utilized. Another aspect we discuss about fuel cell technology, where the natural gas can be used to produce the hydrogen, that is the feed for the fuel cell. Natural gas industry, we discuss from its byproduct to fuel to choice. So, we discuss natural gas engineering aspects where people were not aware about its engineering aspects, where people were not aware about its characteristics as a fuel. So, long time back it was just a byproduct of other process like the coal mines and the oil exploration. When the natural gas is being produced, either it is using locally or before that it is being just flared to the atmosphere. But over the time this became the choice of importance as a fuel, and people are or researcher or the countries are exploring not only the conventional natural gas, but several unconventional sources also, considering natural gas is having a good future as a fuel and feedstock for several materials. We discussed the environmental concern also, that is within the fossil fuel comparison like oil and coal. Environmentally, natural gas is more friendly, it releases no particulate matters, it has less harm to the atmosphere compared to coal and oil. That is why it is considered the most clean fossil fuel energy source to produce the energy. We also discuss about the resources, those could be conventional and unconventional resources. Conventional means the production through this reservoir stream, the upstream sector, where several aspects are involved and the gas is being produced which is naturally stored in the reservoir domain. Unconventional also, the gases are naturally stored in those domain, but the technology has not been advanced up to the level, and coal bed methane, shale gas, tight gas, gas hydrate and other forms are considered unconventional sources. It is believed there is a huge amount of the unconventional energy resources are available at several places, and if those can be exploited effectively, there is a plenty of hydrocarbon energy available still on this planet. After that, we started understanding the origin of natural gas. So, the origin of natural gas is similar to what is the theory for the decomposition of organic matter that has been proposed for the oil generation. Similar theory applies to natural gas production, where the organic material gone through the temperature and pressure history underneath the surface over a geological time scale, where the organic material got converted into coal, oil and finally into the gas phase. To have the resources like the fluid, gas and oil intact in the reservoir domain, there are three types of the rocks are required. Source rock, from where the gas will be producing because of this organic decomposition. Reservoir rock means a permeable rock which is allowing the fluid to flow from one place to another place, and where they are getting a big porous media or a kind of a bank formation from where it can be extracted in a significant quantity. And cap rock, if there is no cap rock in this reservoir rock, then the gas or the oil, because of its own energy, because of pressure energy, will come out to surface by its own. So there should be a cap rock that is holding this valuable reserve underneath, and in a controlled manner can be exploited while we reach to that resource by drilling. That process of reaching to these resources, especially like natural gas, that's found very depth, like around 70,000 feet mostly you will find the natural gas. And to reach that point, it is very important how to find out the site where the drilling should be started. The business of natural gas process start from the exploration. Several advanced techniques have been developed, and those techniques allows to predict very precisely the place where the well should be drilled to produce the natural gas. After producing the natural gas to surface, after finding the natural gas at a particular location, drilling is required. Then well completion process is there. After well completion, production starts, and when production is starting, the gas is reaching to surface, and surface facilities are required to refine this gas and take out the valuable compound, and remaining methane gas can be sent to pipeline or to consumer uses. Some impurities, those need to be separated out also. When we talk about supplying the natural gas to consumer, it is not only measured in terms of volume, but in terms of energy content the gas being supplied to a consumer carrying. It is measured in terms of BTU, sometimes in therm also the energy supplied to consumer is counted. Conventional resources, we discuss about how to classify the gas reservoir based on the gas oil ratio. Gas well, condensate well and oil well are the major classification based on the gas to oil ratio under the producing condition. Future of the natural gas, it is discussed if the transportation or the facilities or the infrastructure can be developed where the natural gas can be utilized at a place of interest from the place of production effectively. A technology or the infrastructure can be developed, it may have a very bright future in terms of the hydrocarbon energy resources. Other technology like fuel cell technology, uses of natural gas in the form of LNG or converting this natural gas to liquid. Before we go to phase diagram, let us discuss the conventional resources one more time. That I said, based on the producing GOR, we can classify gas well, condensate well and oil well. Reservoir, field and pool concept was discussed. So, reservoir is a particular domain where these possibility of these hydrocarbon resources, or in our case the gas resources is high, where we can drill the well and can get the gas out. This one type of the anticlinal trap is shown here. There could be several type of formation underneath. Those allow the fluid, means gas, oil and water, to be trapped, which can be recovered by drilling the well up to the location. Sometimes it may happens the well is not drilled at a particular location, like in this case this is going like this, it is not going to hit properly or maybe little bit far away. Then the decision need to be made, we should stop drilling or should also try horizontal direction. Those are several aspects, those related to the exploration and well completion process. We are not going to discuss those in detail, but what we discuss about with respect to the natural gas, the gas can be produced with the oil. When the well is producing oil, it is natural gas is associated with that well, and that could be in the form of dissolved gas. So, gas is dissolved in the oil. When oil is coming to the surface, because of the pressure difference, gas is coming out of the oil phase, or it is just a free gas, kind of a cap rock formation is there, when the oil is producing, and after that gas is also producing, because that gas was available freely in that reservoir domain. Non-associate gas, that's not carrying the liquid or carrying the liquid in a very small amount, that we called as non-associate gas. Well gas, dry gas are the example of non-associate gas. Condensate gas, gas with high content of liquid hydrocarbons. So, when we are having a gas which is carrying higher hydrocarbon like C7 plus, and when it is being produced to the surface, those, because of the pressure difference, these are getting separated out in the form of natural gas liquid, and we are having the condensate gas type of the reservoir. This is the topic which we are going to cover in today's lecture in terms of the phase diagram. So, before we go to phase diagram, let us understand why phase diagram is required. Phase behavior, understanding of the fluid when it is exposed to different conditions, especially in our case different temperature and pressure condition, how the fluid will behave can be accomplished under the thermodynamics domain, how this particular fluid will go to gas phase or liquid phase can be accomplished with the help of phase behavior study. And based on that behavior, we can classify the reservoir, not only the gas reservoir, but as well as gas and oil reservoir can be classified based on the phase diagram. This is very important because this phase behavior allow us to understand when the pressure is changing. For example, here in the production system where the reservoir pressure is PE, the gas is traveling from PE to PWF, assuming it is under isothermal condition, and when the gas mixture, that is hydrocarbon mixture, but natural gas is a mixture of hydrocarbon and non-hydrocarbon gases. When this gas is passing from a different pressure zone, it will behave differently, not only within the pressure difference in the reservoir domain, but from PWF to PHF and similar at the surface facilities. When it is going to meet the separator, it will behave differently. So, with respect to what is in the reservoir domain and what are the conditions at the separator, if we understand the behavior, how the fluid, oil or gas is going to behave when it is traveling from reservoir pressure to separator. Over the time, the reservoir pressure will also decline. When the pressure is changing within the reservoir, how the fluid that is reserved in that domain that could not be recovered up to that point when the pressure drop in the reservoir, how it is going to behave, will allow us the understanding of fluid phase behavior, allow us to provide or adopt the appropriate mechanism for this hydrocarbon recovery mechanism. So, the hydrocarbon recovery mechanism can be chosen based on the understanding of how the fluid is behaving in a different temperature pressure zone, and the phase behavior mostly understood by pressure and temperature behavior, PT behavior we call it. Broadly classification of oil and gas reservoirs. So, a particular reservoir is producing the oil or gas depend on three primary parameters: what are the composition of that fluid which is being produced, what are the reservoir temperature and pressure condition, and when this fluid is brought to surface, what are the temperature and pressure condition at the surface. We call it like a surface means at the first place the separator, when the fluid is meeting the separator, at what temperature and pressure condition it is going to be. So, these three things, composition, reservoir temperature pressure and surface temperature pressure, decide broadly classification of the reservoir fluid. Broadly we can classify reservoirs as oil reservoir and gas reservoir. We will discuss later on. In terms of the natural gas, the unrefined natural gas that is here in the reservoir travels all the way to surface, and before it goes to consumer, it is just a methane. So, the composition are also changing, and within the reservoir also we will see at the end of this class, we will see when the fluid is being produced from the reservoir, it is assumed like it is producing the constant composition, and the composition of the gas will remain constant throughout the production. But if it is a different type of the reservoir where the phase separation is happening, the composition will also get changed, and when the composition are changing, everything designed based on the composition will get affected. Another application of phase behavior, and where the phase behavior is going to help us, is production prediction. So, we can predict the production if we understand well how the fluid or the gas which is being produced is going to behave in future when the pressure will decline in the reservoir. So, before we start understanding the complex behavior of our complex system, that is natural gas, a mixture of hydrocarbon and non-hydrocarbon gases, let us understand the thermodynamic or the phase behavior of a single component. Any component which is present in a system, and we are going to understand its behavior under different temperature, pressure and volume, that we call the PBT behavior, how it is going to be. In a 2D diagram, we always choose two parameters. So, for example, here pressure versus volume, for any component it says how we are going to achieve bubble point and dew point. Bubble point means first bubble of gas appears, and dew point last drop of liquid. Beyond this dew point we are having the gas, and on the other side before bubble point is reached we are having the liquid. So, if we see here, for example, we are having this pressure, liquid is there, and when we are reducing the pressure, what we are going to see? First the bubble point and then a constant line, and then we are going to hit the dew point, when there, in this case only volume will change, not the pressure, and once we reach the dew point we are having the last drop of liquid is appearing. We see here the first bubble of gas and here the last drop of liquid. After that we are having the gas. In this region, in between, in this region of bubble point and dew point, we are having the mixture which is in equilibrium. Generally we understand the PT behavior, we choose the PT behavior instead of the PV behavior, and where we can say with respect to pressure and temperature how a particular single component is going to behave when it is having the solid and vapor region, liquid and vapor region, solid and liquid region, where it will be in a solid form only, when it will be in a liquid form only, when it will be in a vapor form only. Our interest with respect to natural gas is in this region when we are having the liquid and vapor. So, let us understand that what we discussed, when we are changing the pressure or the volume, either we are reducing the volume or reducing the pressure, or the increasing the volume or increasing the pressure, or any combination of pressure and volume, we can change the phase of a component. It can go from liquid to vapor, vapor to liquid, or a condition where it is existing equilibrium between gas and means both gas and vapor and liquid phases are existing together. So, for a single component, again with respect to pressure and temperature, we can see how fluid behaves when we are having temperature and pressure. When the fluid is exposed, single component fluid is exposed to different temperature and pressure history. So, we are having this line, that is called the vapor pressure line. On this on one side of the line we are having just a liquid phase, on the other side we are having the vapor phase, and the point where on this line where the both liquid phase and vapor phase are existing together, and from this point when liquid is going to convert into vapor because of the changes in condition, this line will call the bubble point curve, and by any mean vapor is going to change into liquid, this line will call the dew point curve, and the point C here is the critical point above which the gas and liquid cannot exist together. So, and this point on the temperature scale is called the critical temperature, and on the pressure scale it is called the PC. Bubble point curve, when we are having this bubble point curve changing liquid to vapor phase, and that can be done, for example, we are going in this direction from pressure to volumes, pressure to temperature. If we are increasing the temperature at a constant pressure, we are going to get the phase change from liquid to vapor, and similar when we are reducing the temperature, the fluid is passing this line or vapor curve line, it will change from gas to liquid. So, that can be accomplished. We can change the phase of a single component system just by changing temperature and pressure, and this phenomena is just represented by one line, that is called the vapor pressure line, which accounts for both bubble point line as well as dew point line, and the fluid characterized by a single point C that says beyond this point there is no chances where the gas and liquid can exist together. If we extend this further and say for a two component system, if we are having the two component system, here I had shown the diagram for multi component system, assuming there are only two component system, what exactly happens? The vapor pressure line is not a single line, or the bubble point and dew point, they get separated, and one side you will be having the bubble point curve and other side we will be having the dew point curve, and in between bubble point curve and dew point curve there is kind of a region we call this saturation envelope or the phase envelope, where both liquid and gas phase are existing together. There will be several lines, we call them the quality lines. Those represent the amount of liquid in terms of the volume. When we are at a particular location within this envelope, we can draw that quality line and can say how much percent the two component mixture is in the liquid phase and how much is in the gas phase. The point, critical point will be here, and that above which the gas and liquid cannot exist together, the definition will be the same for this system also. Two more point comes here, that is the Kirchendov-Bohr and Kirchendov-Therm, that we are going to discuss separately. So, for a two component system, the vapor lines just get spreaded and becomes kind of a envelope where we can draw several lines for the representing the volume. Bubble point curve, the first bubble, so when we are changing the condition, similar thing will happen. When the liquid is reaching this point, the first gas bubble will appear, and when we are going down inside of this, for example, we are going like this straight line, let us say at a constant temperature isothermal condition, we hit this point when we are having the first gas bubble will appearing, and then further we are going, the amount of the gas phase is increasing. Similar from this point, when we are reaching the dew point, the last liquid drop will appear, and after that if further reduction is happening, we are in the beyond the or below the dew point curve line, we are having only the gas phase. When it comes to hydrocarbon mixture, it represents different unique system. We will discuss that thing. For a pressure and temperature history, when the hydrocarbon mixture is exposed, we get two terms, that is a Kirchendov-Bohr and Kirchendov-Therm, and both are different than the critical point, if you see the critical point here. So, the Kirchendov-Therm simply says the highest temperature at which the two phases can exist here. So, this is Kirchendov-Therm. Beyond this point, if the temperature is higher than this, we are having only the gas phase, does not matter what pressure is there. Similar on a Kirchendov-Bohr point, where we are having this point, beyond that we are having only and only the liquid, does not matter what temperature it is. Corresponding to this Kirchendov-Bohr, we are having Kirchendov-Bohr temperature, and similarly with respect to Kirchendov-Therm temperature, we are having Kirchendov-Therm pressure also, that will help to characterize the system. So, this is critical point, we are seeing several quality lines, those are getting merged to this critical point, and when they are merging at a critical point, it means they are reaching to a critical point, and the bubble point curve and dew point curve, they are separated. Again we are having the envelope here as for the two component system. For multi component system also the envelope will be there. Quality line again will represent the percent of the liquid phase of that mixture when we are exposing the material to different temperature and pressure history. Other aspects of that can be understood. For example, the bubble point curve for the hydrocarbon mixture, that says it separates the pure liquids. Here we are having the liquid from the two phase region, that is our two phase region from here to here. Below the bubble point curve, so when we are reducing the pressure reaching to this bubble point curve, and when we are further reducing it here, here the first bubble of the gas will appear, and when we are going further, the phase will go to two-phase region, or the liquid will go to two-phase region, where both liquid and gas will be existing together. Similar for the dew point curve, from here we are entering in the two-phase region, and in that two-phase region we are having the condition where the gas will get converted into liquid. So, here we are having just gas, and here we are having the liquid. If we understand this for the hydrocarbon mixture, that I said, if we know the composition, we can draw this phase diagram. This phase diagram, the shape of this phase diagram depends on the composition. If the composition are changing, the shape of this envelope will get changed, and there are very different shape we will see in coming slide when the system is producing different type of the hydrocarbon mixture. But this is just a representation where it says we are having the bubble point, dew point, both bubble point and dew point are going and merging at the critical point. By doing this, there is an envelope got created. Within that envelope, we are having the both gas phase and liquid phase. Can be classified just based on this understanding what type of the reservoir it is. If we see, this is one of the example, we are having some specific reservoir fluid composition. With the help of performing the experiment, we could establish this bubble point curve and dew point curve for different temperature and pressure history. We got this envelope, inside this envelope we got several quality lines. Now, if we see, this is a critical point. If the reservoir temperature and pressure on this part, or especially reservoir temperature on this part, we are having the oil reservoir. So, it means when the reservoir temperature is below the critical temperature of a hydrocarbon mixture, we are expecting it is a oil reservoir, and when it is higher than that, we are having the gas reservoir. Oil reservoir also further classified in several segments like black oil, volatile oil, condensed means near critical point oil. Similar on the other side, the gas reservoir are also classified as gas condensate reservoir, dry gas reservoir, bed gas reservoir, and that depends on where the reservoir temperature and pressure are falling on that envelope, and based on this chart we can say at the temperature and pressure condition the fluid will behave like this type of the reservoir fluid. For example, we are having this black oil. If P is always greater than the bubble point pressure, it will always remain in the liquid phase, and we are having just a black oil in this region. When it is going down, the phase will get changed. We are more interested in the natural gas class on this right hand side, where we are having this gas reservoir domain, and in that case we can see this is a critical point. From here we are having the gas reservoir, and this is a dew point curve. If we are understanding this in detail, we can say we can classify that as a dry gas, wet gas, or gas condensate, and the gas to oil ratio, degree API, and color of the fluid which is being produced. Sometimes, like for example, in condensate reservoir we are going to produce the liquid also. So, the color, degree API, and gas to oil ratio can tell us which type of the reservoir it is in the domain of natural gas. It is condensate, it is well, or it is wet gas, or it is a dry gas reservoir. We will discuss this one by one. So, we understand now the dew point, and the dew point is here and bubble point curve is here on this side, and within this envelope we are having the solution gas drive. So, if reservoir temperature, pressure condition are falling in the near to bubble point curve, we can say the solution gas drive reservoir it is there. We are having the gas that is dissolved in the oil, and that is kind of a driving force for the oil to be flow from reservoir to surface. And when we are close to this dew point curve, we are having the wet gas. It means some of the component of the gas phase got converted into liquid phase, but still it is majority in the gas phase, and we are having the reservoir of a wet gas type. Here I had shown some diagram for like how a typical PT behavior. So, we go further, we see the PT diagram for a multi-component system. It is just a representation where it says the envelope may take any shape depend on the composition. So, here the liquid phase is just here, like when we are having more than 2000 psi, and the gas phase is here when we are having more than significant temperature. Between this we are having the quality line two phase region where the percent of liquid and gas is changing. Critical point may be somewhere here. If we see for a particular component, for example, the ordinary black oil, we see the shape get change because the composition of the oil which is produced as a black oil varies from C8 to C100 and more than that. So, hundreds and thousand compounds are there. If we do the PBT or PT phase behavior study for the ordinary black oil, we will see like the shape of the envelope will be very different, and this is a pressure path line in the reservoir. So, when we are in the reservoir domain, we are at one point. When we are going to produce, the oil will also travel from a different path region, or over the time when the reservoir pressure is changing, the pressure the fluid is going to experience may be different. Considering the isothermal condition, we will see the oil will hit this bubble point line, and then we are having the two phase region, and at the separator when this even the black oil is going to reach at the separator, whatever the amount small or large amount dissolved in the oil phase will come out automatically. So, we will be having the two phase production even the reservoir is just a black oil reservoir. Now, focus is on gas type reservoir. So, we are having three types broadly classified, three types of the reservoir: dry gas, wet gas and condensate reservoir. There is another near critical point reservoir, or sometimes the condensate reservoir is also called as a retrograde condensate reservoir. Let us classify it in just three broadly part: dry gas, wet gas and condensate reservoir. The same diagram is here that we discuss here. Now, we can extend our study further. What we can say, this is a bubble point curve, this is a dew point curve, both are merging to a critical point, and you see there is a region between the critical point and Crichton-Therm. The region is called the condensate region or the retrograde region, and this is always covered by the shaded region. This is a very unique phenomena that is exhibited by the hydrocarbon mixture only. We will discuss little later. So, I think the understanding is very clear. Based on this diagram, we can say if the temperature is too high, and that happens when we go underneath around 17,000 feet or more than that, the temperature is such high, mostly we get the gas reservoir. So, if the reservoir is at a very high temperature beyond the Crichton-Therm, we are going to get only the gas reservoir under the reservoir condition. Again, the gas will travel from that high temperature, high pressure reservoir region to surface. It will be facing different temperature and pressure zones. So, we have to specify the condition. That condition says under the reservoir condition beyond the Crichton-Therm, the gas is always in the gaseous phase, and we can say this is in the dry phase. We will discuss again the dry phase. When we come down here between the critical and Crichton, we are having the condensate, and when we are within this envelope, when we are within this envelope somewhere or the near the dew point curve, we are having the wet gas reservoir. So, the phase envelope of natural gas can be very different depending on the composition. If you are changing the composition, the phase behavior will get changed, or the envelope which represent how the mixture, hydrocarbon mixture is going to change when we are having the different pressure and temperature exposure will get different shape. Let us see here for a wet gas, we are having this PT diagram where it says here is the liquid, here is the gas, and when we are going to get the wet gas reservoir, let us say we are starting here. The reservoir pressure temperature is at point A. We know at point A this is just a gas because it is beyond Crichton-Therm temperature, and beyond Crichton-Therm temperature we are supposed to get the gas reservoir. Now, the pressure will change pressure will change because the production is happening, and when the production will happen, over the time the reservoir pressure will depleted. And when we assume there is no change in the temperature, that is not going to be the case, but let us assume reservoir is under isothermal condition. When we are reducing the pressure, what we will see, we are going to go like this, and that's happens. We see here in the dry gas reservoir, we start the producing here, we are saying there is no change in the temperature, only pressure is reduced in such a manner that the pressure or the line that is drawn for this changes in the pressure is by any mean not going to the envelope. It is not going to the envelope side, temperature is not changing, just it is going like this. We are going to have only the dry gas reservoir. So, the dry gas reservoir primarily it contains the methane. This happens because the composition of the gas or the product are in such a manner, they had created such envelope where the reduction in the pressure at a constant temperature is not going inside the two-phase envelope, it just getting produced like this. And the compositions are primarily methane with little or no heavier compounds present. There will be some compound present, but not in a significant quantity. Mostly dry gas reservoir produce a small amount of the water. Surface temperature falling outside the two-phase envelope. So, that I said even the surface pressure temperature condition are falling outside this envelope. So, there is no mean the gas is going to cross the dew point curve and becoming two-phase system. No formation of NGL. When it is not crossing the dew point curve, not forming any liquid substance, it has no natural gas liquid present in it. While what happens in the case of wet gas reservoir, when we are going down, now pressure is changing. We are going down, pressure is changing because of depletion is happening, because fluid is traveling from reservoir pressure to wellbore pressure. Now, when it travels to surface, the temperature may get also change. When the temperature is changing, the path line reservoir or the pressure or path line will shift like this. And when it is shifting, crossing the dew point curve, reaching the two-phase region, it is going to emit the liquid out of the gas, and we are going to have the liquid drops out once gas reaches the surface. The surface condition, when we said here, for example, the separator where the temperature and pressure are within the envelope. Within the envelope, it means the gas will go to liquid phase also, and we are going to get the two-phase system, and that gas produced under that condition is called the wet gas, and the reservoir is called wet gas reservoir. It becomes very important when we want to run the gas well under the wet gas condition or under the dry gas condition. That can be controlled by precisely understanding the phase behavior. We will discuss later on how it can be useful and how it can be a drawback. In the next, when we talk about the retrograde region, in retrograde region what happens between the critical point and Crichton-Therm, there are several quality lines, and when the fluid or reservoir condition are between this critical temperature and Crichton-Therm temperature, when pressure is reduced at a constant temperature, it goes through the two-phase region and intersects several quality lines. When it happens, a retrograde kind of the behavior occurs. When we reduce the pressure, the gas is going to hit the dew point curve, it should go to liquid part. Now, when we further reduce, it goes to vapor part. See here, like from here it is going to 15% liquid, now it is going to 10% liquid, means some of the liquid got re-vaporized, and this is a unique phenomena that happens only in the case of the hydrocarbon mixture, and because of that, because of this retrograde nature, this kind of the reservoir are also called condensate reservoir because they produce the liquid, and sometimes they also called as a retrograde condensate reservoir, because not only they are producing the liquid at the surface, that happens in case of the wet gas reservoir also, we are going to get the liquid on the surface, condensate on the surface. in case of wet gas reservoir, but in this case of the reservoir, in the retrograde kind of the reservoir, we are going to get very complex system where the liquid will further get revaporized when it is going to hit the low pressure region, and becomes very complex system if we are not having a good understanding about the phase behavior. We are not understanding when the gas is going to liquid and when liquid is going to gas, when we are changing just a pressure. And imagine when we are going to change both temperature and pressure together, the line may go very differently depend on the temperature and pressure, as we did for the wet gas reservoir. When wet gas reservoir, the pressure was declining isothermally. When we said no, temperature is also changing, the quality line or the pressure path line just change and enter in the two phase region and cross several quality lines. Between the dew point and the dew point where liquid revaporize is the region of retrograde condensation, that's shown by the shaded part. Liquid condensation form a condensate bag around the valve. So, what exactly happening? From the reservoir high pressure, the fluid is traveling to valve. Now, it is going to hit the low pressure region because the flow is happening because of the pressure drawdown. If pressure drawdown there, then only the flow will happen, and because of this pressure changes, because the pressure is changing, assuming isothermal condition, we are going to get some of the gas getting converted into liquid, and when this liquid is getting converted near the valve region, it is going to form a oil bank near the valve region, and when the oil got accumulated near the valve region, it is going to reduce the effective permeability for the gas passage. When gas is not able to pass, it means it is reducing the recovery of the gases, or other way it is ceasing the production. Production is not happening at the desired rate because the effective permeability for the gas got reduced. A bank of oil got formed near the valve region. Another problem comes in the liquid loading. When this liquid just goes through the valve and the gas is coming, it is not having enough energy to carry over this liquid started getting accumulated. While the reservoir is a dry gas reservoir, but when it goes to surface facilities, the production facilities, in between it pass through the several temperature pressure zone, and similar happens in the valve. Within this valve, liquid got accumulated and the gas just not having enough energy to carry over this liquid. Under that cases, several actions should be taken, like injecting the gas or setting the well for some times, let it get equalized, or some other means should be adopted to reduce the liquid loading. That conversion from gas to liquid may be useful also, because the reservoir, those are having such kind of the behavior, those can produce liquid while they are classified as a gas reservoir. Liquid is having more value than the gas. So, if we are not able to take out that liquid which got converted near the valve region, for example, we are going to lose the quality material inside the reservoir. So, we want that liquid is getting produced to the surface, but at the same time we do not want the production is getting ceased. That is why it is always a challenging task when we deal with natural gas production system. So, in summary, phase diagrams study allow us to understand the hydrocarbon recovery mechanism. Those should be adopted to have the better production prediction, as well as having the profit, running the well under the profit condition. Gas reservoir be understood, dry gas reservoir, wet gas reservoir, condensate gas reservoir, how to produce the reserve from a reservoir which is initially beyond the Kirkcondine temperature, means it is completely a gas reservoir, how it can go to wet reservoir and how it can go to condensate gas well reservoir. And when it is condensate gas well reservoir, how effectively it should be produced. So, we are not losing the valuable product inside the reservoir. Similar, we are not going to cease the production also. Understanding the near well bore gas condensate flow is thus very complicated and important to optimize production of gas condensate reservoir. So, the gas condensate reservoir is one of the complex domain of natural gas production. Here we can see like natural gas is being produced. Here this is the region where the liquid loading may happen. Here is the region when the oil bank may get formed here. based on the understanding, several action can be taken to account or to understand the effective production mechanism that can be adopted. With this, I think our natural gas introduction chapter ends, and we are going to discuss some of the technique those will be required when we are going to understand several aspects of natural gas production, processing and transportation. For example, in the previous slide, when the natural gas is getting produced from this region to PWF, from PWF to PHF, we set up the mathematical equation. Sometimes the mathematical equation, or most of the time the mathematical equations are complex in nature, because the fluid properties will get changed based on the local temperature and pressure condition. As the fluid or the gas is being produced, it is going to face different temperature and pressure condition, and because of that the properties will get changed. When the property is getting changed, the parameters those are depend on the properties will also not be constant. With this, I would like to thank you for watching the video. We will meet the next week. Thank you. Thank you very much for watching the video.